Hello. Our presentation today is focused on determining restaurant inspection grades. In New York City, each restaurant must undergo an inspection where they are ultimately given a grade based on health inspections. Grades are determined by violation scores. Each violation increases a restaurant's score, thus lower scores yield better grades. The breakdown is that scores from 0 to 13 are an A, 14 to 27 are a B, and 28 and over are a C. If a restaurant achieves the letter grade of an A on the first attempt, they follow a more off-leash inspection cycle, wherein they would only have to be inspected 11 to 13 months later. For restaurants that receive below an A on their first attempt, they have 7 days to rectify their errors ahead of a second inspection. At the point of the second inspection, they can be reevaluated for any of the 3 tiers. If they maintain the categories of B or C, their cycles are more restrictive, forcing them to be inspected again in the next 3 to 7 months. Our inspiration for this project was research done utilizing Yelp's ratings from an API to determine inspection grades. Other studies we found were seen to use features of zip code and food or cuisine categorizations to predict inspection grades. For our project, we'll be looking to make an inspection prediction model that was more accurate than ones that we found online. We thought that with more detailed information, specifically about the property types that restaurants are located in, we'd be able to achieve our goal. Thus, the questions we asked were whether the property a restaurant is located in will affect the inspection grade, and if so, based on the factors of area use, property value, property age, and restaurant cuisine, what is a likely inspection grade that would be received? To answer these questions, we looked at 2 datasets. The first being a dataset from the Department of Health and Mental Hygiene in New York City with over 400,000 rows and outlines restaurants and their inspection grades, their violation codes, and their cuisine types, among many other features. One problem with this dataset is that many grades in the grades column are missing. Furthermore, there can be many rows for each inspection. The second dataset is from the Department of City Planning in New York City with over 800,000 rows and outlines property types and their descriptions, such as whether they are mainly retail or office spaces, for instance. Some of the main problems we found in this dataset is that there are a lot of missing data, and there are outliers in columns such as the year built column. However, both datasets contain a BBL column, BBL standing for Borough Block Lot, which presents a unique location index, and it will be highly critical in that we will use the BBL to join the 2 sets. Our first attempt to process and train this data had many hiccups, but it provided insightful analysis and results from which we were able to recognize problems in our data and model and build upon. The first step we conducted was data cleaning. We extracted 9 out of the 26 columns from the inspection dataset and 15 of the 90 columns from the PLUTO dataset. Secondly, we merged the 2 datasets according to the BBL identifier. Next, we processed the missing data based on its pattern. For the missing and not random values in the grade column, we kept them since no grade meant a failed first inspection attempt and was relevant to our project. On the other hand, for missing at random values, we dropped them since they made the score of this inspection useless. From there, we filtered the data by narrowing it down to rows with inspections conducted in 2019, and from there took the final grades of that year for a restaurant. We ended up with around 86,000 rows. Now, with our clean and joined dataset, we are ready for the next step, algorithm implementation. To prepare the dataset for training, we divided the data with an 80-20 random split. We then trained a linear regression model, training each feature separately. Thus, in this first attempt, we only implemented one algorithm and did not train features together. The root mean square error we got from each feature didn't differ as much as we expected, and the mean square errors were all around 74. Which also was not a good enough result for us to confidently use this model, and thus we knew changes had to be made. In this next slide, we have provided a heat map that we created to better understand each feature from our aforementioned linear regression model. The heat map shows high correlation exists in some features, which shows the redundancy between them and helps better explain the less than satisfactory results we got in the previous slide. Also in the heat map, we can see there is multi-collinarity between the attributes, which also helps account for the poor performance of the linear regression model. Furthermore, we saw here that outliers existed in the scores attribute, which we had used for the training label.
So when it comes to our second attempt, based on the issues and findings previously, we decided to adjust our analysis approaches and restructure the data cleaning process to get cleaner inputs. Regarding the data cleaning, we dropped rows missing every data in InSpec dataset, but used another approach, this time filtering for the inspections completed on or after 2017. It only kept the 3 most recent inspection records. Also, we removed rows having letter grades not discussed in official grading criteria this time. Meanwhile, we dropped the nulls in PLUTO, and then we did the same extraction as before for the columns. After making sure that both datasets are cleaned, we join the data on BBL and get around 100,000 rows of data points. Then we also dropped rows having abnormal values in year build column. This time we did data exploration in advance to understand what we could expect from implementing the algorithms. Again, we plot a correlation heat map and found that comparing with last time, there are fewer variables being highly correlated with each other. But the issue of multi-collinearity remains. So we assumed that linear regression might not be that helpful here, but we still implemented it as a benchmark as for previous attempt. Also, we found that in our dataset, 90% of grades are A's, as the distribution of the letter grades appear to be similar even after the dataset is aggregated by borrow or by cuisine type. We believe that our model needs to have an accuracy of more than 90%, or else it is no better than randomly guessing the inspection grade to be A.
In our second attempt, we implement new methods in this time. First of all, we implement data division and also the cross validation on both the numerical and categorical dataset. These 2 datasets are meant to train and test by different algorithms, and we will talk to this later. And the second one is about feature engineering. So we transfer the letter grades into numerical encoding, and also we implement some feature importance analysis to see which features matters the most in our prediction. And the third one is about the algorithm we implement this time. There are 3. First, linear regression. The second one is logistic regression. And the third one is random forest. Let's take a look about the result we got from linear regression first. So for the cross validation, we got root mean square at 3.8, which is really better than the result we get from the first attempt. And we also applied the feature importance analysis in this one. As we can see in the right plot of this slide, there's a lowest root mean square error when the features number is 66. So actually we use the model trained by these 66 features according to the importance analysis and test on the dataset, in which we get the root mean square error at 14, which is not bad as well. And we also actually look into the 66 features, and we find out that there are 3 kind of features that matters the most. First one is like property features, and the second one is cuisine types in this area, and the third one is about borrow information. Okay, so let's look into the result from logistic regression now. We got cross-validation accuracy, and we also apply feature importance analysis, but this time we found out that all features matters equally, because as we can see from the right plot, the accuracy didn't differ a lot. So we decided to keep all the features and use this model to test, and we got the accuracy at 0.89. Last but not least, the random forest, and we got the cross-validation accuracy using random forest at 0.95, which is really great comparing to previous studies and the previous result we got. And we also run the feature importance analysis and use those like 22 features we got from the analysis to train the model and also test. And finally, we got the accuracy at 0.69.
The results give us the answer that the property features along with the cuisine type and borrow of the restaurants are significant determinants to their inspection grades. And given the accuracy performance of the 3 models we've implemented, the random forest prediction model stands out as it allows us to predict inspection grades at an accuracy rate of 96%. This is way higher than a previous study on an inspection dataset using naive Bayes classification algorithm, which ended up with an accuracy of 62%. We think the difference is that that study only used zip code and food type to predict restaurant inspection grades. Besides, another research project using the Yelp API found that there was no direct or clear correlation between inspection grades and ratings. So it granted the high accuracy performance to the model we chose and the property features of the restaurants we included for prediction. The feature engineering and thorough data cleaning also contributes to achieving this high accuracy.